For 2D forces, we're going to take the concepts of two-dimensional motion and Newton's laws of motion, which include forces. In 2D forces, there are x components and y components, the horizontal and the vertical. Also, we have forces involved. Forces are the component that cause motion to begin or cause motion to stop. There's one equation, Newton's second law. Force is equal to mass times acceleration. If the acceleration is 0, due to either constant velocity or the object being at rest, then the net force on the object is equal to 0. So in a free body diagram, we can consider all of the horizontal forces or all of the vertical forces and determine if there is motion in that direction or 0 motion. For an object being pulled up at an angle, we can take the sine and cosine of that angle to break down that particular force into its components. Then when we do the sum of the net forces, those become part of the sum of the horizontal forces or the sum of the vertical forces. The x component, the horizontal component of the force, is calculated by taking the force times the cosine of the angle. The vertical component, the f of y, is calculated by taking the force times the sine of the angle. If in the free body diagram to the right, the box is being pulled and lifted to the right, there's motion to the right. So in the horizontal, the sum of the forces will be the f of x, or f cosine theta, equal to the motion. Now we can either solve for mass or acceleration or whatever's being asked for from this equation. The sum of the forces in the y direction are a little more involved because in addition to the y component of the angle to the right, there's also the normal force, which is up, and the weight of the box, mass times gravity, which is down. Since the object is not jumping up and down, its motion is 0. Now we can use this equation to solve for the weight, or the normal force, or the y component of the force at the angle. Objects on an incline also have horizontal and vertical components. But because the normal force is perpendicular to the surface, we refer to the components of weight as being either perpendicular to the surface or parallel to the surface. Again, we can do the sum of the forces in the vertical and the sum of the forces in the horizontal. The angle of the incline, due to some fancy trigonometry, is going to be equal to the angle of the vertical weight force versus the perpendicular to the surface, the normal force. The net sum of the parallel forces include the parallel component of weight. If the box is sliding down the incline, that's equal to ma. If the box is at rest, however, the parallel component of weight will be set equal to 0. The net sum of the forces in the perpendicular direction include the normal force, which is in the positive direction, perpendicular to the surface, minus the perpendicular component of weight, which is negative because it's in the opposite direction. And since the box is not going to jump up and down on the ramp, then that is set equal to 0. What we find is that that normal force is comparable in magnitude to the perpendicular component of the weight. The parallel and perpendicular components of weight are calculated as weight times the sine of theta for parallel and weight times the cosine of theta for perpendicular. The elevator problems. When on an elevator and it is accelerating upward, then the normal force increases when accelerating downward, the normal force decreases. The effect of that is that the weight registers higher when accelerating upward, and the weight registers lower when accelerating downward. The formula when going up is going to be the normal force minus mass times gravity in the opposite direction will be equal to mass times acceleration, where acceleration is positive. So essentially the acceleration of the elevator adds to gravity times the mass, and that tells you the normal force. But if the elevator is going down, the net force equation includes a negative component for acceleration. These equations can be rearranged to actually solve for the acceleration, or if given an acceleration, used to solve for the normal force, which will be the reading on the scale. For problems that have an object hanging and there's tension in the wires, if there are two wires and the angles are equivalent, then you solve for one side and then just double it. So the equation is 2 times the tension sine theta, that's the y component of the tension of the wire, minus mass times gravity, the weight, in the opposite direction. And since it's not moving, that'll be set equal to 0. Now we can rearrange the equation to solve for the mass of the object or the tension in the wire. If the wires are at different angles, where one is at an angle theta and the other is perfectly horizontal, you still resolve the sum of the net forces in the horizontal and the vertical. For the vertical, there is no vertical component of the T2 wire since it's horizontal. So we only need the Ty, which is T1 sine theta, minus the weight in the opposite direction, equal to 0 since it's not moving up and down. Then we can use that equation to solve for either the mass or the tension. For the x components, we have T cosine theta, which is the T sub x for the first tension, minus the T2, which is in the opposite direction, again set equal to 0 since there's no motion side to side either. And finally we have the force of friction. The force of friction is calculated by multiplying the coefficient of friction times the normal force of the object. The coefficient of friction is a unitless number that is a ratio describing the surface that is in contact, creating the friction. This three-variable equation can be rearranged to solve for any of its components, the coefficient of friction mu or the normal force. Friction is the force that acts in the opposite direction of motion. Therefore, it is a horizontal component. Because of direction, the force of friction in the negative direction will be equal to the mass times the acceleration in the direction of motion. The sum of the net forces in the y direction would be the normal force, positive because it's up, minus the weight in the opposite direction down, equal to 0 since the box isn't jumping up and down. The same holds true even if the object is on an incline. Now the sum of our horizontal forces are the parallel component of weight, which is weight sine theta, minus the force of friction in the opposite direction, which would equal ma. The net forces in the y direction will be the normal force minus the perpendicular component of weight, which is weight cosine theta, equal to 0 since it's not jumping up and down. And then essentially the perpendicular component of weight is equal to the force, the normal force, just like it was before without friction. It's just now we tend to use the friction equation to find out what the normal force is before we get to this point. Remember, there is essentially one equation. Force is equal to mass times acceleration. Everything is just a variation of that one equation.